Okay, so let's continue. Well, let's give a formal introduction on what we want to do with a hash table. So given that we have a table T and a record X with the key as a symbol and the static data. So what we want to do is at least we want to support insertion, deletion, and search. And though they have to be very fast and hopefully they can be done with a constant time. Okay, so for the keys, well, in the remainder of this lecture, we are going to assume that the keys are just the natural numbers. So you may ask, how about uh, a key is a float number? Or how about the key is a string? So if the key itself is a float number, well, we can do some simple trick to force that to be integers. So for example, if we have a float number which is 12.4, if we just throw away all the values after the decimal, and then 12.4 will become 12. So we can just use the 12 as the natural number as a key. Or if you want to do this a little bit harder, you can keep the first n digits. So let's say just we do the n as 4. So 12.4. So if we keep the first 4 digits, and then it will be 1, 2, 4, 0, right? So again, we are changing that to 1240, and it is again a natural number. And how about a string? So if we have a string, and then we can use the ASCII number or the ASCII value for each of the character, and then we are casting a string into integer again. So the point I'm trying to make is, well, we are not assuming all the keys are natural numbers. However, for other data types, we can transform them into natural numbers. Okay? So, well, suppose that we have a range of the key from 0 to m minus 1, and then, well, we assume that all the keys are distinct. And one of the easiest thing we can do is, since we have the keys range from 0 to m minus 1, and all those values are natural numbers, right? So how about we just create a list with m slots? So what I mean is something like this. We create a list with m slots, and for each of the slot, if it is already used, and then there will be a value somewhere. So if the 0 is used, and then let's assume that, well, the value is here, and then it is young, for example. Okay, so the slot 0 is used, and then it references to a value called young. And then if we have used the 2, and then 2 is used again, and then we assume it is a 10, for example. So when we use a slot, and we can simply use the current slot and then refer to a value. So that is the insertion, right? So if we want to do a search, that's simple again. So if we want to check whether the slot 3 is used, and remember, we are dealing with a list. So for a list, access is a constant time. So we directly go to the slot with the index as 3, and then we see, okay, the slot 3 is not used. So, well, to do a search, well, it is also a constant time. And the last thing, how about the deletion? So later, if you want to take back the slot 0, so what do you need to do? You only have to break this reference, and after this reference is already deleted, the next step will be you can also delete the value here. So you delete the reference, and then you delete the value, and then your work is done. So in this case, well, consider what we just discussed before. We want to have the insertion, deletion, and search done in constant time. And actually, with just a list of m slots, this can be done, right? So it seems that we have already find our first solution. However, the first solution, we call that direct address table. So for the first solution, direct address table, we say this is not a good solution. So why? The reason is we are assuming that the m itself is a reasonable value. If the m gets arbitrarily large, and then we will have a big problem. So how about that if we have the m and then the m is a 32-bit integer? So 32-bit integer, and this is really a reasonable guess of the possible size of the integer supported in a programming language. Okay, so in this case, well, remember we are creating a total of m slots. In this case, well, m is 4 billion. What does that mean? This means we have to create 4 billion slots. So in this case, well, if we come back to this one, well, this table here, we are not talking about 1,000 slots, we are not talking about 5,000 slots, we are talking about 4 billion slots. That's really a lot. And if you really have such a big memory, you can do that. Remember, when you initialize this such a big table, and then you have to initialize all the values to be null or to be none. And in this case, well, even initializing this kind of table can be a big problem. So how can we do that then? So the problem is we are creating a symbol table, and this symbol table is way too big, and this is a problem. So the concept of the symbol table itself, that's okay, but we have to somehow make the table size manageable. Okay, so the solution is, even though we can have a big variety of the possible keys, and the range of the keys can be really large, however, we want to make the m small enough. So the concept is, well, even though the universe of the keys could be very large, however, when we are creating a table from 0 to m minus 1, so for the table says, again, the table says it's m, but the table says should be much smaller than the possible range of the keys. And this is the hash function. Hash function is how we can map a key to a corresponding slot in the hash table. Even though the keys can be very large and we can have a big range of the keys, when we take a key and then apply the hash function will tell me which specific slot in the hash table can we find the value, and then the hash table itself should have a reasonable size. Okay, so this is the concept of the hash function, and I will see you in the next video.